So now we can start talking about unusual values. So unusual values we've already talked about. One definition to know that something is unusual is that the probability is less than or equal to 5%, right? If a probability of an event is less than or equal to 5%, we know it's unusual. However, what if we don't know anything about the probabilities? Well, we have a second definition to determine unusual values. So unusual values are typically values that are relatively far away from the mean, right? It's going to be far away from the average. If we're talking about heights and you're really, really tall or really, really short, the probability of that occurring is going to be really small. So that would be an unusual event. So what we typically say is that if it's further away than 2 standard deviations, then that's going to be considered unusual, which means that if it's within 2 standard deviations, that's going to be usual. So let's look at this. So if we have our mean inside, right, on a normal distribution, so if we are 2 standard deviations away on either direction, so let's think about that empirical rule. Do you remember what percentage of data is within 2 standard deviations of a normal distribution? So it's 95%, right? Which means that the outside is going to be a total of 5%. And if you remember we talked about the probability of something occurring is less than 5%. That's kind of where that's coming from. So to check for unusual values, what we need to do is we need to determine the lower bound and the upper bound. So the lower bounds, we said it's going to be 2 standard deviations below, right? So that's taking the mean and subtracting 2 standard deviations. Or taking the mean, subtract a standard deviation, subtract a standard deviation. This is very similar to what we were talking about with the empirical rule. For the upper usual, we're going to take the mean and we're going to add 2 standard deviations. Or take the mean, add a standard deviation, add a standard deviation. So if the data value is outside of the bounds that we've created, it's going to be considered unusual. So this is one way to do it. I'll show you a different way to do it in a second too. All right, so problem number 3 on the word problems. Using a chocolate chip count for 40 chocolate chip cookies, the mean is 24 chocolate chips and the standard deviation is 2.6. So would 30 cookies be considered unusual? So if we have our mean of 24.0 and we add 2 standard deviations to it, what do we end up with? So we would get 29.2 chocolate chips, right? So 2 standard deviations above would be 29.2. And then if we subtract 2 standard deviations, we end up with 18.8. All right, so everything inside of here is considered usual. We can even erase that and make it look a little easier. So we want to know, is 30 chocolate chips considered unusual? Well, where's 30 on this number line? 30 would be right here. So it's outside. So yes, this would be considered unusual. And would it be unusually high or unusually low? Well, it would be unusually high, right? Because it's higher than the maximum. 30 is bigger than that maximum value. So it's unusually high. Let's do another example. So the mean adult weight pulse rate is 67.3 beats per minute with a standard deviation of 10.3 beats per minute. Is a pulse rate of 48 beats per minute considered unusual? So again, unusual. We don't have anything with probabilities. So we're going to have to use our mean and standard deviation rule, right? We're given the mean, we're given the standard deviation, so we can use that rule to figure out if it's unusual. So we know what goes in the middle is 67.3. So if we want to go 2 standard deviations above, we got to add 10.3 2 times. And when we do that, we end up with 87.9. So 2 standard deviations above, 87.9. And we got 2 standard deviations below. So we subtract 2 standard deviations. And when we get that, that is 46.7. So everything inside of here is considered usual. So we want to know, is a pulse rate of 48 considered unusual? Well, according to here, 48 would be inside, right? So this would be considered usual, not unusual. All right. So I remember I said there are 2 ways of doing it. So that is one way of doing it. So we can just talk about the mean and the standard deviation, be good as gold. Another way to do it is to talk about the z-score. So remember what we talked about, if we go back to our definition of z-score is the number of standard deviations away from the mean, right? It's the number of standard deviations from the mean. So if we know that unusual is outside of 2 standard deviations, then if we have a z-score that's bigger than 2, then or less than -2, we know that we have an unusual, right? So another way to think about it is unusual means that you have a z-score greater than 2, because that means you're more than 2 standard deviations away, or a z-score less than -2, because again, that means you're more than 2 standard deviations away on the other side. And then a usual value would mean that the z-score is between -2 and +2. And again, if you don't like this, don't worry about it. If the other way made more sense to you, you can just fast forward through this video. But since we have talked about this, let's look at the other way. So we want a z-score of 30. So if we go back to our problem, right? So z-score, we have the value minus the mean divided by the standard deviation. So the value was 30. The mean is 24.0. And the standard deviation is 2.6. So we do 30 minus 24 divided by 2.6, and we get about 2.31, which is definitely more than 2 standard deviations away, right? So since it's more than 2 standard deviations away, this is considered unusually high, right? Because it's higher than 2 standard deviations, which if you notice, the exact same answer that we got. And you can kind of, if you wanted to do another graph, right? Remember, for z-score, the mean is always 0. So 2 standard deviations is 2. 2 standard deviations below is -2. And then we have a value that's 2.31, right? So outside. All right. Likewise, if we want to do it problem 4 the other way, right, we just need to figure out what the z-score is. So it's the value minus the mean divided by the standard deviation. This time we want to know, is 48 considered unusual? So 48 is our value. Minus, we have our mean. So the mean is 67.3. And then divide by the standard deviation. Standard deviation of 10.3. So when you subtract and then divide, you end up with about -1.87. Now, does it make sense that we have a negative z-score? Well, yeah, because it's below average. That's perfect. Now, notice this is within 2 standard deviations, right? If you draw your line, 0 is in your middle, positive 2 is as far out as it can go on the right, negative 2 is as far out as it can go on the left, and we are right there in the middle. So this would be considered usual because it's between negative 2 standard deviations and positive 2 standard deviations. Well, 2 standard deviations below and 2 standard deviations above. All right. Like I said, 2 ways of doing that. If one of them made more sense than the other, don't worry about the other way. Just whichever way made sense to you, do it that way. All right, let's talk about percentiles. So percentiles, we don't need to worry too much about it, but we'll talk a little bit. So percentiles, so if you were talking about the kth percentile, you're talking about this symbol, P sub k, probably the percentile of k, the kth percentile, excuse me. So this is the value such that k% of the observations are less than or equal to the value. So if you're in the 95th percentile, that means you are smarter than 95% of people. You're smarter or as smart as 95% of the people, right? You're on the top end. So example number 1. Jennifer received the results of her SAT exam. Her math score of 600 is in the 74th percentile. Interpret this result. So we know that if she's in the 74th percentile, Jennifer did better than or equal to 74% of the students who took the exam. Right? So she did better than average. So if we did, if we kind of drew a graph of that, if this is where average is, she would be kind of up here. Right? This is the 50th percentile, right in the middle, 50%, so she's more than halfway. What percentage of people did better than her? So if she did about 74%, right, better than or equal to 74% of the students, what percentage of students did better than her? Well, 100% of the students would be all of them. So if we subtract the 74 that she did better than, we see that 26% of people did better than her. So this side of the table would be 74% that she did better than. The other side would be the 26 that did better than her. All right. That's all we really want to talk about for that section for now. We'll bring it back up. All right. So there are 3 or 4, it's 3, percentiles that are more important than the others for now. So the first quartile we say is Q1, and this is P25. So P25, if we go back to our definition, we said that PK was the kth percentile. So P25 would be the 25th percentile. So this divides the bottom 25% of your data, right? You're better than or equal to 25% of people. From the top, so what percentage of people did better than you? 75%, right? 100 minus 25. The second quartile is going to be Q2, and this is going to be P50, or the 50th percentile. So this is going to split up the bottom 50% and the top 50%. We'll skip this next one for a second, but then the third quartile, of course, is going to be Q3, which I'm sure you can guess by now is going to be the 75th percentile. So it divides the bottom 75% and the top 25%. All right, guess it's got to stick for a second. Cool, all right. So if we look at a line with all of our data, right? So if this line consists of all of our data, so we can split up our data, right, into 4 parts. P25 or Q1, P50 or Q2, and P75 or Q3. Now, the interesting thing about P50 is that it's in the middle of all of our data, right? Do we remember a word that also is considered the middle of our data when we order it from lowest to highest? So this is just the median. Yeah, so the median is a fancy word for the 50th percentile or the second quartile. So if you notice, right, if we have these 3 values plus the smallest number, which is the minimum, and the biggest number, which is the maximum, you can get a pretty good summary of what our graph looks like, right? With these 5 numbers, you can get a pretty good summary of what these data or all your data looks like. Speaking of 5-number summary, I wonder what this is. Yeah. So this is exactly what we just talked about. The first number, as long as you have these 5 numbers, you're good to go. So the first one is the minimum value. The second one is the first quartile, or Q1. The second one is the median, right? Also known as the second quartile. Then we have the third quartile. And then we have the maximum value. So, as long as you have these values, you are good to go. All right, so on a separate video, I'm going to walk us through how to do this problem. Actually, we can do this now. Yeah, let's just do it now. We don't need a separate video. All right, so these are all the values that we want. We want to know what is the 5-number summary. So for this section, just like with the last video, last section, we talked about 1var stats. Well, that's what we're doing for this section as well. We're going to use 1var stats. So we're going to go into our calculator. So here's the calculator simulator that I'm using. Might take a little while to get up. All right, so we're going to clear it, clear our history. So again, you can follow along with me. Hopefully you have on your paper, this was problem 3, so you have all of the data next to you. So what we want to do is go to stat, enter, right? Stat edit, that's where all of our data is going to go. So if you need to clear out everything, you go all the way up to highlight it and hit clear, enter. All right, so now we just got to type in all our data. So 73, 75, 80, 87, 89, oop, go back up, 87, there we go, 89, 92, 93, 94, 95, 96, 97, 98, 98, 101, 101, 102. Yeah. Make sure that you do you type all these in right. If you notice, I accidentally typed in some of them incorrectly, but I caught myself. If you don't catch that, you're going to get stuff off. So after you type everything in, right, we want to go to Stat, over to Calc, 1var stats. We only have one list, so list is L1, good. Freak list is blank because we don't have a second list. So then we just hit enter to calculate. Now, again, we have our mean, we have our standard deviation, but what we want is our 5-number summary. So if you scroll all the way down, you'll notice the last 5 numbers is min x, Q1, median, Q3, and max x. Now wait a minute, those look familiar. Yeah, this is our 5-number summary. So it just tells it to you right there. So as long as you know how to use the calculator and one var stats, these problems should be pretty easy. So we see that our 5-number summary is going to be 73, 88, 94.5, 98, and 102. And that's it. We're done. Yay! If you want partial credit on the test, a good way to do that would be to write out one var stats and then write the actual numbers you see. So a good way to, if you wanted to get some partial credit, because again, there's not a lot to do, right? With this last test, you had a lot of options for partial credit because you could write out specifically the numbers that you're multiplying. In this case, since we're using our calculator, there's less partial credit to do. So what you could do is you could write out one var stats, tell me that's what you're using, and then for the 5-number summary, just write out specifically the 5 numbers, right? So you can write, it said min x was 73, q1 was 88, mid x was 94.5, q3 is 98, and then max x is 102, right? Or median, yeah, not min x. So this is a great way that you can tell me you know what you're talking about, right? Because if these numbers are off, that means you just type something in correctly into your calculator, but I can still give you some partial credit because you knew to use one var stats and you knew these were the 5 numbers that were important. Yeah, so always a good thing for partial credit if that's something that appeals to you. All right, hopefully not too hard. Let's do one more problem. So problem number 6. So once again, let's find the 5-number summary of this data. So let's do it. So again, we're going to clear everything, go back to stat, edit. We're going to go all the way to the top and clear out our list. So clear, enter. And we're just going to type it all in, right? So 19.95, 23.25, 23.32. There we go. So you go ahead and you type in all your values as well. Oop, got that one wrong. There we go. All right, and after you're done, it might be a good thing just to go through and make sure that you typed in all your numbers correctly. Oh, yep, I already messed up. So 30.35, there we go. Because again, very easy to just type in an incorrect number at one place and then all your stuff's messed up. All right, after everything's typed in, go to Stat, over to Calc, one var stats, only using one list. Ooh, oh, well, messed up. All right, there we go. So if we're only going to round to like 2 decimals for all of them, right? Here's our answers. So again, if you want to know what the partial credit would look like, you could say one var stats. So min x is 19.95. Q1, after you round it to 2 decimals, would be 26.06. The median is 30.95. Q3, 37.24, max X, 54.63. All right. Hopefully not too hard. Everything making sense. Cool, cool, cool. All right, so let's move on to box plots. So box plots, or also known as box and whisker plots, you might have heard that one instead, is basically a graph that consists of all the lines extending from the 5-number summary. So if you want to know how to construct it, so I'll show you what it looks like as we construct it. So first thing you want to do is determine the 5-number summary. Right? Need to know what the 5-number summary is to be able to graph the 5-number summary. All right, so what you want to do is on a scale, you want to make sure to include the minimum value and the maximum value. So determine where the minimum is and where the maximum is. Then you want to construct a box extending from the first quartile and the third quartile. So wherever it is, first quartile, third quartile, we're going to make a box around it. Then we're going to draw a line at the median, also known as Q2, right? So wherever the median is, we're going to draw a line down. But the only thing you need to do now is making a lines extending from the box to the minimum value and the maximum value. And that's it. So notice there is no line going through the box, right? That is not happening. Our box is on the outside. There's no horizontal line in the box. Now, you may also, this is typically how I draw it. I think in our book, in some books, you just see dots at the maximum and the minimum. That's okay too. So it can either be a dot or it can be a line. I'm not picky. You can do whatever. As long as you don't have a line going through the box. That's a no-no. All right. And this box can kind of tell us what kind of distribution we're looking at, right? So this one, for instance, would be pretty normal. Everything's about symmetrical. All right. So let's do a box plot of problem number 5. So we already found our 5-number summary. So we just need to draw it on a graph. So we can have, we can start with any number as long as it's no more than 73, right? So we can just start with 73, or we can start with 70, or whatever we want. So some people want to start with 73, so let's just start with 73. And we just need to go up by some increment, right? It could be 2s, 5s, 1s, whatever. So let's just go up by 5s. So 73, 78, 83, 88, 93, 98, 103. All right. And since 103 is more than 102, we're good. That's as far as we need to go. All right. Well, 73 is right here. So we got our minimum. You can even write the 73 there if you want to just make sure everyone knows what you're talking about. 102 is going to go right before the 103. And then we have 88 and a 98, right? 88, 98. And then we see that 94.5 is going to go, so we make a box around these two numbers. And then we see that 94.5 is going to go somewhere here-ish. So then we just write out the extensions. And there we go. We've done a box plot. So what kind of distribution would this be? It's definitely not normal, right? This is not symmetrical. So we can see that most of the data is on the right side. So it's getting pulled to the left. So this would be left skewed. All right. I don't want to. I want to make sure that I didn't mess up the video, so we're going to stop here, and then I will pick it up in part 3.